University of Technology, and I'd like to talk to you about our work on comparing the ERA 5 forcing data set versus the somewhat older ERA interim forcing data set and what the impact is on hydrology. So normally you would have your second slide be all the names. I just decided to put a photo up there. These are all the co-authors that were involved in getting the results you're about to see. And I specifically want to mention Jeroen Aerts, who couldn't be here today. Jeroen is, he's the main author on this, and he's my PhD student. And he's doing a PhD in computational hydrology. So along his 4-year track, I'm expecting him at some point to generate some hydrographs by running some hydrological model based on some forcing. And one of the main questions that starting PhDs, but researchers in this room, we've had the topic come up a few times, look at is which forcing am I going to use? And what's the impact of that on my results? Recently we used back in Europe we used the ERA interim forcing set a lot for our hydrological studies. And recently ECMWF released ERA 5, which is newer and better scale and according to ECMWF at least. And we wanted to look at what's the impact for hydrology, which would mean that you would have to run it on 2 forcings and get 2 hydrographs. But if you want to look at what the impact is for hydrology and not for some hydrological model, ideally you also want to run it on other models, preferably models made by other research groups, which gets you in this case already 4 hydrographs. And this brings me to my central point, I think, and my pet peeve over the last few years. If you Google hydrologist, and I like to do Google image search, this is what you get. Basically, this is us. Our image is pretty good. We're the ones that get to go outside. But especially the people in this room, I think we all know that if you're lucky, this is 5% of your time. And the other 95% of your time will just be in a cubicle, in an institutional setting somewhere, munching on the data that you gathered in that 5%, or a lot of talks about that as well, munching on data that other people have gathered, or that's coming from satellites or from pre-existing forcing sets. That munching on data that we do, we of course do in hydrological models that are coded in computer languages. And I'm pretty sure that most people in the room didn't pick the language by considering what was the best language for that problem at hand. You probably picked the language you were taught in grad school. So that means that the knowledge we get is codified in these different programming languages. So our knowledge of these hydrological systems are codified in different programming languages. And I, for one, being old enough to be taught in MATLAB, cannot read Fortran code. And I hopefully never will have to. This makes it really hard for researchers to run each other's models. It's going to be a problem if it takes a postdoc or a PhD 3 months to get the model of the group next door working on their computer. And that is one thing that we started to fix in our eWaterCycle project. We built a piece of technology, it's called gRPC for BMI. It uses Google's RPC as a translator between languages, and it uses BMI from CSDMS as a basic interface to models. And what it allows us is from a Jupyter environment, make calls to model objects that are running in Docker containers, and the Jupyter programmer doesn't see what the language of the model is. And what we've done for a collection of models already, models that are often used in this community, we've already put them in those containers. So there's, for example, a model available in Fortran, and I can run an analysis in a Jupyter notebook, accessing that model, getting results from it without having to read a line of Fortran code. And I could also even couple that model in this environment to, for example, a model that's running MATLAB. But by the way, we're running Octave. We're not allowing people to run MATLAB on our open source, fair by design system. MATLAB should be phased out. But this allows you to couple models in different programming languages made for different uses from a common environment without having to be an expert on the nuts and bolts of the code of that specific model. We were pretty happy having built this. I wanted to share that with the community. So we had a workshop this spring in Leiden, beautiful town in the Netherlands, a fair hydrological model where we invited hydrological models from all over the world to come and work with us to do a comparison of all these different models. And that brings me back to my photo slide, because these were all the participants of that comparison. There's representative from age research groups representing hydrological models from all over spectra, but I have to emphasize 40% of the people in this photo are research software engineers from the Netherlands eScience Center, which is how eWaterCycle got funded, and they've been instrumental in both building this and getting this to work. We have this in a very nice location in Leiden where all the walls were either blackboard or whiteboard. So we split up in groups for the different models. We had Waveflow from Deltares, Sumo, Flow. Oh, one of the nice things, we had both Hype and WFlow, which means you have Deltares and SMHI, like kind of consultancy companies that normally are not in one room together. So in this framework you can more easily also compare those kind of models. Split up in groups and have all groups work on getting those models containerized and become part of our system. We broke up in nice breakout sessions, everybody behind computers. It was just a working day a week. We kept a nice whiteboard matrix of our progress during that week. Over the week we filled this in with tick marks, except for one thing. If you look very closely, I apologize for my handwriting, but the upper layer says pre-processing era 5 input, and a W means work in process. And at the end, pre-processing era 5 was still work in process at the end of a long week of work. Because what we underestimated in this very basic setup of what computational hydrology is about is this simple error. How do you get from era 5 to something that your model can read? And I think that if you look inside your own research group, you probably have a standard way of doing pre-processing. And it most likely is something like this. It's somewhere on an old shared drive. There's a copy of a forcing data set. And then if you want to make that ready to run through your typical model that you always use in your group, there's probably an old shell script made by a postdoc long ago, which has 3 or 4 parameters that you can tweak, but you've never looked at the code in the last 7 years. And we're building eWaterCycle to be fair by design. I like it that one of the previous speakers mentioned open by design. We're extending that into the entire spectrum of fair software and data. And doing pre-processing in this way is not fair, because there's science in that script that you're not making part of the scientific record. So typically, what would you want to do in a pre-processing step? You probably want to download some data. You might need to regrid it. You probably need to do a sub-selection of the region you're interested in. Most likely, there's a derivation somewhere in there to get from parameters to other parameters. Potential evaporation is a classic one. And then you have to write it in some specific output format for your model. And if you're doing a comparison with different models, this is maybe for one model, but another model might need some shapefile selection, because it's based on catchments instead of pixels, different regridding, different derivation. And this already exists. It's called eWaterCycle tool, or system model evaluation tool, and it's developed for the climate science community to look at the differences in the big circulation models. And this I want to get back to is one of the advantages of working with those research software engineers that work on more than just hydrological projects. Dr. Drost, one of the co-PIs on eWaterCycle, was also one of the PIs on eWaterCycle because he's also in a climate project. Some of the research software engineers in our team are on humanities projects, and anytime I'm going to come up with, we need some kind of crawler to look at which models exist, so we need to go over the web. They answer with, the humanities have already fixed that problem for a different domain. Maybe you want to use that instead of rewriting the code from scratch. Using eWaterCycle allows us to take different data sets and in a controlled way do pre-processing. eWaterCycle only takes a small recipe file that says do this standard form of regridding, do this standard form of selection, and only if you really need something that's not supported, you can also say, and do this Python script at the end to get it to my preferred model input format. And that is all fair by design. eWaterCycle is open source available, the little recipe file is readable by humans, so in this way we can do pre-processing not only of the one data set that we need, but with multiple data sets and prepare them for multiple models. What we contributed as a team to eWaterCycle is that it's now not only ready to work with standard climate models, but it's also ready to work with standard hydrological forcings, especially ERA interim and ERA 5. So what we've basically built over the last 2 years is an environment, currently in Jupyter, where you can talk to hydrological models through our gRPC for BMI, and where you can, fair by design, do pre-processing of hydrological data to get to those hydrographs. Now, what does that look like? I have a slide with code. This is a very simple example of what it looks like. You have a recipe file that you can load in. Those recipe files are templates that we already provide, so it's rather easy to do that. You can change the things in the recipe, in different periods, whatever, and then you run eWaterCycle to get your forcing. One of the things you could, for example, do is change it to a different region, provide a different shapefile. Once you have that forcing, you can just make a model object if you want to run a model. It just points to a model location, which is a Docker container. You initialize it using the BMI command, and then you can just run it. So model.update is just run one time step, and in the lowest line you can see model.getValue, in this case discharge. And in this way, I could just change out model location and point it to a different model from a different group and do the exact same experiment on that model. And that's also what we've done. As an example, we're having a look at the Meuse Basin, because we're from the Netherlands. And one of the models we used was Marmot, which is developed in Bristol. It's a model suite, but we're explicitly using the most simple model that they have. It's a one bucket model, just to prove a point. So if for Marmot, we're treating the entire Meuse Basin as one bucket, and we'll say to eWaterCycle, please pre-process the inputs that are needed. We're getting something like this for ERA interim and ERA 5. Luckily, the timelines match almost. There's like slight improvements in ERA 5, but there's differences, and WF would say there's slight improvements. So this becomes the inputs to run Marmot with, and then we get hydrographs as output. So we can look at what the impact of ERA 5 and ERA interim is for, in this case, the Marmot model. It's not surprising that a one bucket model does not perform really well for a catchment the size of the Meuse. We also support a distributed model, WFlow by Delta Hades, and if you run eWaterCycle for WFlow, you get distributed input. So this is the ERA 5 versus ERA interim input if you want to run WFlow. And if you then actually run the model, you get nice distributed discharge output. That's where we're at right now. We got almost five of the 8 models that were in the workshop in Leiden working. We're working really hard to compiling that all in one big comparison paper. Once that is done, we'll be bringing that to the community and opening this platform to the entire hydrological community to do their research fair by design and work with each other's models. On behalf of this entire team, I'd like, and well, the institutes that they work at, I'd like to thank you all and we'll take a question if there's time.